am Dr. S.P. Harsa, Faculty of Mechanical and Engineering Department at Roorkee, going to present today the lecture 3 of the strength of material subject. So in my previous lecture, we discussed about the two main components of the stresses, like the normal stress component, in which the force as well as the stress components are perpendicular to the area of concern, while the other thing is the other component was the shear stresses, in which the forces as well as the stress setups which are there within those object are parallel to the matter of this area. So meaning is that, you see, like we discussed about the two major components, but sometimes it is not fruitful to just discuss only about these two stresses, because as we have seen that there are the derived stresses like the bearing stresses, like the tensile, like the compressive stresses, like the torsional stresses or the thermal stresses. So these are all the derived stresses. So for if you want to analyze any of the component or the object, we need to see that actually what other like the parts of the stresses are there and how they are applying, because the basic reason of the stresses inducing in an object are like what is the point of force of application is. So how you see the force applying on those objects. So today you see we just want to see that actually that what stresses are there. So first thing is that the analysis of the stresses, in which we just want to see that actually what is the general state of the stress at a particular point. So as we have seen, the stress at a point in a material body has been defined as a force per unit area, that is the internal resistances per unit area, or we can say the internal intensity of the resistive forces. But this definition is somewhat ambiguous, because you see we have seen that it depends upon the what area we consider we concern or we consider at a point. So you see actually what the area is there, whether the effective area and the force application, what the exact relation is there in between those things. So now you see we just take a general case in which there is a regular body is there, and we have chosen one Q point in the interior point of this body. So we have seen in this figure that actually this is my the body is there in the body somewhere, not exactly at the center, but somewhere you see we have chosen a point Q. This body is in equilibrium position under the variety of these forces, you see. So these force applications are there, but we assume that these forces are well set up because of the internal resistive forces. So you see we have chosen all three axes, and we know that actually the forces are coming from the various the aspects and at various variety of the angles. So you see either F1, F2, F3, F4 they are coming, you see, and here we have chosen all the compressive forces. Okay, so now you see we just focus on these things, that actually this what are the forces which are coming and what are the internal resistive forces which are inducing or which are resisting from this body because of the inherent property of the body. They are well set up, and that is why this body is under equilibrium. Now you see, to analyze the stresses, the internal intensity of the resistive forces, to discuss about those things, what we are doing here, now we are passing a plane which is exactly perpendicular to the x-axis. So now you see here our matter of area concern is the x, or we can say now we are playing in the x domain. So whatever the forces are coming, our main nature of the field or the domain is x-axis. So now let us pass a cutting plane through a point Q, exactly wherever it is the point Q is there in this object, perpendicular to the x-axis as shown in this. So now you see, you have seen in this figure that actually all the forces are being applied to the object, and at this particular point now we have chosen a small segment, and the area of this segment is delta A, and whatever the forces are going, because we have chosen three different directions, so in those directions the forces are going like in x direction, which is perpendicular to the x-axis dF, but the other two forces, because you see we have chosen the x-axis and this force is perpendicular to the x-axis as we have seen in this figure, like here you see this one, but other two forces like dFy, dFz, they are not perpendicular to this concerned axis or the x-axis, they are parallel to the x-axis. And this is my dAx if the x-axis is there, day if the y-axis is there, and dAz if the z-axis is there. So here you see this is my matter of area is the matter of area concerned. This is my dFx, this is my dFy, this is my dFz. So if I see these things that okay, these three forces are playing in the x domain only, then what the stress components are. So now you see in this, the corresponding force components can be shown like that, like if dFx is there, then as we have discussed that actually wherever the force component is perpendicular to the area concerned, then we have the normal stress component. So here we have sigma xx into dAx, that means dAx is the area surrounding to the point Q when cutting plane is perpendicular to the x axis, as we have discussed. Okay, so now you see here, as far as the x component, the force component in the x direction is concerned, we have dFx is sigma xx. That means you see here in x direction we have normal stress because of the perpendicular axis, but the other two force components like dFy and dFz, in these the forces are not perpendicular to the area concerned. So here you see, the normal stress components are not being set up within the object or outside of the object, that means the surrounding part. So here you see, the parallel stresses are there, that means the parallel forces are running just to the layers of the object. So here we need to consider here that the shear stresses are there, and that's why you see here we are denoting here the shear stress component is tau xy. Tau xy means here tau is the shear part. Now the subscript says that x into y, x is the domain, as I told you. Now we have chosen the x domain and y is the force direction, because here we are concerned about the dFy. So force is going in the y direction, but the nature of the object is there in the x domain. So here we can see that actually, like this one, here we have chosen this x, which is the domain, and this force is going towards the y direction. So as I told you that actually the shear stress is not the axial stress, shear stress is a plane stress. So this is my xy component, in which we can say that the shear stress is there, but the area which I have chosen, the small area, that is the dAx. Similarly, if we have chosen the y axis, this dFz, in which also we have seen that actually this tau xz, x is the domain in which the force is there, all the segments are there, but the force is going in the direction of z. So we have the shear component here. So means that you see, if we have chosen a small point just in the x domain, we found that there are three variety of the stresses are there. One is the sigma xx, tau xy, and tau xz. So these three components are there, these three forces are there in the x domain. Similarly, you see, if we just go to the y axis, that means in the similar way it can be assumed the cutting plane passed through the through the point Q perpendicular to the y axis. That means now we are playing in this y domain. Okay, and now whatever the forces are there which are being set up irrespective of the internal or external forces, we just want to check that actually how these forces are acting in this plane. The corresponding force components, as you see here, that at point Q, in this particular figure here, this is my area of the matter of area concern. This is the perpendicular force dFy, this is the parallel force dFx and dFz. So you can see that, you see what the corresponding stresses are there, as we have discussed. So you see here, first of all, the dFx. Now in the dFx, we know that we are now tau of y into x into day. Day is, the area of surrounding at point Q where the cutting plane is perpendicular to y axis. That means you see here that now our domain is y, while the force, first of all, if you are talking about dFx, that means the direction of the force is in x direction, domain is y. So obviously now the parallel stress components are there, that means there is no perpendicular things are there. Now you see the shear stresses are always dominating in this kind of thing. So dFx is nothing but equals to tau times y into x into day. Similarly, you see if we are going to dFy, which is nothing but, you see, this is my y domain and it is just perpendicular to the y dFy. So obviously we have the normal stress component. So dFy is nothing but equals to sigma yy into day. And similarly, you see if you are talking about the dFz, which is, you see, nothing but equals to tau times y into z into day. So you see here we have the area in day direction, means the y direction, as well as you see these other two components, means the tau yx or tau yz. These are the shear stress components working in y domain but going in the x as well as the y direction respectively. Okay, so means you see here either in x domain or y domain, or similarly if we are thinking about the z direction, means it can be considered that the cutting plate passed through a point Q perpendicular to the z axis. Okay, in the z axis, you see now this is the area like which we are concerning, the point Q is there in between that, and DAZ is there because it is now perpendicular to the Z axis. So now you see the force is just going perpendicular to this axis. This is the DFZ, while other two forces, they are well set up, either irrespective of the external or internal forces, well set up in the parallel forces. So you see, if we resolve these forces in terms of the stresses, then we would find that you see here that dFx is nothing but equals to tau times Zx into dAz, dFy is tau times dZy into dAz, and tau Fz is sigma Zz into dAz. Means that now we have two shear stress component in x and y, because as I told you, the tau Zx, because we are working in the Z domain, which is exactly this, like you see here, the inclined plane towards this. So this is my Z plane, but in these you see this is my sigma Z, or we can say Fz. So I have sigma Zz, means the both domain as well as the force direction in the both sides. That's what you see, the normal stress component is there in the Z direction, while the shear stress component is there in the other two domains, because we other two directions, because we have the same domain and we have the two different direction of the forces, like in x and y. So we have the shear stress component tau Zx and tau Zy, and you see dAz, because we are concerning about like the area which is perpendicular to the Z axis. So dAz is the area surrounding the point Q, like because we are concerned about the point Q when the cutting plane is perpendicular to the Z axis. So it's a clear meaning that you see from the foregoing discussion, it is amply you see clear that there is nothing like stress at a point Q. Means we cannot say that okay, now like the force is there. Force is a very the phenomena in which we are just taking, as I told you, that actually what is the directive part is there. That means what is the point of application of these things are there. But it cannot be true for the stress, because once we apply the force, there is something going on in the molecular way. So how these once you apply something like this one, so once you apply the force on any object, this force is now okay, but what has happened suddenly then in the object? We have to be very careful, because you see, if you want to design something, once the impact is there or even the regular forces are there, we have to be very careful that actually what has happened inside the object, whether you see only the stresses are there, or whether you see whatever the internal resistive forces are there, they can sustain these kind of this impactive forces or the regular forces. So rather to discuss about a simple stress at a point Q, we should discuss that actually what is the combination of the state of stresses, means what is the combination of the stresses, or we can say the generalized state of stress at particular point. Means you see, it is the combination of various stresses. Thus it becomes imperative to understand the term of state of stress at a point Q. So like you see here now, if we go in that, then therefore you see it becomes easy to express state of stress by scheme as discussed earlier, you see, because we have seen that actually there are three like the corresponding force directions are there, dfx, dfy, dfz in the x domain. Similarly we have in the y domain, similarly we have the z domain of these forces, three different forces, dfx, dfy, dfz, and we have found that in every domain these nature of the forces are being different because of the different directions of the stress components. That's what you see, we can see that if you are choosing the three-dimensional part, then almost there are 9 different components are there. That means you see if we want to define a stress at a point, the single stress doesn't give you the clear understanding of the real phenomena. So what we need to do here, we need to check that how these generalized stresses are being formed within those things. So the state of stress as depicted earlier is called general or triaxial state of stress that can exist at any interior point of a loaded body. So that is the the generalized definitions of those things, and it gives you the new phenomena of the stress, that stress, we cannot say that stress is a scalar quantity or a vector quantity, because in the vector only you see just the similar directions are there, or the scalar there is only the magnitude is there, but in that you see it is now you see it is going in the 3 into 3 matrix, or we can say it is going in the different directions as well as the domains. So now we need to define the stress in a different manner. So now you see now like as there are two different types of the coordinate systems as we discussed like in the first lecture, that one is the Cartesian coordinate in which we have chosen x, y, z, and other one is the polar coordinates in which we have chosen like we are generally using r, theta and z. So first, if we discussed about the Cartesian coordinate system, about these stresses, because as we have seen that actually these stresses are being set up differently in these different directions, like in like in x, y, z. So now just consider these things, that in the Cartesian coordinates again we are using three axes x, y, z, and these three axes are mutually perpendicular to each axis, and they are like this one. This is my x axis, this is my like the y axis, and this is z axis, which is perpendicular to the xy plane. Okay. And now whatever the stresses are being set up, which you can see even here, like you see where this one, the x is there, this is y is there, and the z is there, which is perpendicular to this xy plane. Okay. So now here we are also considering the unit element of the parallelepiped. That means you see like why we have chosen this parallelepiped, or we can say this unit cube, because in the cube we have the 6 faces, and all the 6 faces are having the unit length, and it is symmetrical in all directions, because means that you see here, if we are talking about the 3 direction x, y, z, so it has 6 faces, so 3 faces which are with the x, y, z direction. In the frontal side they are having the unique feature just exactly like the rear part, means it is a symmetrical object having the unit width, and whatever the stress components are there, we can assume, because if you have seen previously that we assumed that whatever the area is there, that is the uniform area, because if irregular bodies are there, then what we need to do, we need to discretize the domain into different domains and then integrate those things, because you see as we discussed in the previous class that there is the stress concentration is there, means you see if we have a weakest region, or we have some sort of like the cracks or some different kind of like the domain is there, that means the stresses are being more because of the force per unit area is there. So area is always like an important part if you want to compute the stress. So here also you see the basic reason to choose this unit cube or parallelepiped is simply because it is symmetrical in all 3 directions, or we can say all 6 faces. You can see this one, this is 1 phase, 2 phase, 3 phase. So these 3 phases which we can see, and the just opposite to these thing like this one, or back of this, or lower of this, the other 3 phases, they are exactly similar to this diagonal. That means you see like this is a symmetrical object in which we can simply assume that how these stresses are being set up. Now as we have chosen 3 directions, as we have, you see x, y and z, so we can see that actually this sigma x, okay, which is a uniaxial stress because it's a normal stress component. So this is sigma x, this is sigma x, okay, and in y direction this is sigma y, and this is the sigma z, which is a perpendicular to the area of this xy plane. So these 3 you like the small element which we have like chosen here of any material in this all 3 stresses, the normal stress components are well set up, and these are set up within these corresponding directions as it is shown in this diagram. Now you see the other coordinate system, as I was discussing about the cylindrical coordinate system. So this is you see the different domain now which we have is r, theta and z. That means you see we have just used like we have just used here the z coordinate, because the z coordinate is there exactly in that, but we have the other 2 coordinate because of the cylindrical system which we are using here. So we have the radius of that as well as the this theta, which is the angular displacement of this. So here meaning is that we have, if you see this diagram, then we have this z axis, okay, which is exactly perpendicular to the other 2 axes. That means we have this one. Again, if you go to this, we have the z axis, okay, and we have this r axis. So this is z and this is r, and this is the theta, which is just revolving in this side, okay. So now if you take a small segment of the cylindrical coordinate, then you will find that we have, as I told you, the sigma r. So this is sigma r, which is a uniaxial stress in x direction. So we have the normal stress component in sigma r. We have another this you see like the normal stress component, that is the sigma theta, and in the vertical direction as we have chosen the z direction, so we have sigma z. So you see here, either irrespective, if you go to the previous slide, then we have the sigma x, sigma y and the sigma y top and sigma z. So here the directions are just like this Cartesian way, or if you go to this slide, then you will find that we have r theta z, where the sigma r is there in this direction. So we have to be very careful while we are choosing that which you know, like the coordinate system we are using. So if you are using the xyz, then xyz, the z is just perpendicular to this xy plane. That means this one, this one. So irrespective of this or this is my xy plane, and this is just perpendicular to this direction or that direction. While here you see I am just taking the vertical component of the z, and r is the circumferential radius of the cylindrical coordinate, and the theta is the angular location of these things. So if you see these things, then you will find that so these components and these other components, how they are being set up within the cylindrical body. So this is like that. So this is sigma theta, sigma z, and sigma r is there. Thus in the cylindrical coordinate system, the normal stress is, because here we are only concerning about the normal stress component where the force is perpendicular to the concerned meter of area, is the normal stress, that is the component acting over element, is being denoted to sigma r, sigma theta, and sigma z. So here you see, you know, like these two coordinate systems are well accepted in the universe, and that's why you see either we can go, if the regular geometry is there, that means you see the square is there, or any of you see the rectangular bar is there, it's pretty easy for us to analyze those stress components in Cartesian coordinates. But if we have, you know, like the surfaces, like if aerofoil is there or any radial geometry is there, this kind of thing, and if you want to analyze those things, like you see, you know, like the this turbine blade is there, or aerofoil kind of, you see the aerodynamic blades are there, or any kind of, you see this geometry, always we need to choose the cylindrical part, the polar coordinates. We can say this is polar coordinates also. So the polar coordinate system in which the r, theta, z is the coordinate system is, okay. And then you see, if you are, you know, like going for the sign convention of that, as we discussed that actually that the stresses are being inducing due to the application of force. So what is the point of application of the force is, if we have a regular or irregular geometry, it does not matter, you see, but if the force application is pulling, means you see the tensile forces are there, always you see there is an extension is there, because it always, whatever the forces are there, the internal forces which are being set up within the object, they are always tries to resist that pulling. That means they are well set up to opposite to the pulling side. So we can use the sign convention for the tensile forces or the tensile stresses as the positive, while in the compressive, because it just try to opposite the tensile way. That means you see we are now compressing the object. So obviously whatever the forces, internal forces are set up within the object, they are always try to repel that part. Means you see we have the whatever the resistive forces are there, they are just coming the nature of these forces are just towards the outside of the object. So we need to choose, because of the compression is there, the compressive forces, or we can say the compressive stresses as a negative way. So you see these are if we are talking about the normal stress component, then always we need to choose that the tensile stress as positive and the compressive stresses as negative. But in that, you see, you know, like if you just go back to these this concept, we found that either if you are working in x domain or y domain or in z domain, the stress components were sigma, if it is in x domain, then sigma xx, tau xy, tau xz. That means you see in these three stress components, there are two subscript. One is you know, like if you are talking about the sigma xx, then it is xx or tau xy or tau xz. So in that, the first subscript indicates the direction of the normal to the surface. That you see what exactly the direction means, what is the domain of the surface is, how the cutting plane is cut. If it is cut in perpendicular to the x-axis, that's what you see in the first case. We have seen that all those first subscript sigma xx, tau xy, tau xz is always x is there, because the cutting plane is perpendicular to the x-axis. Or similarly, you see if you go to the y direction, then you will find that the cutting plane was perpendicular to the y-axis. Then that's why you see these three force component, either this dfx, dfy, dfz, which you can compute as this tau yx, sigma yy, and tau yz. Okay, means the first subscript is y, because the cutting plane was perpendicular to the y-axis. Or similarly, you see if you go to the z, then also the similar terms are there for dfx, dfy, and dfz, like we have the tau zx, tau zy, while sigma zz. Okay, so means the first subscript just gives you that what exactly the direction of the normal to the surface is. Means you see what the domain is there, or what is the area of the concern is. But second subscript indicates the direction of the stress, or I should say the direction of the force. That what is the point of application of force is resistive force. Okay, so here you see, you know, like we can see that if domain as well as the directive stress or the directive force is in the same direction, then we have the normal stress component, because there is no parallel, like the forces are there in the system. That means there is no shearing is there, only irrespective whether we are pulling or we are compression, only these two uniaxial part is there, because it's the same axis, the domain as well as the force in the same, means we are working in the same domain, and the force is also there in the same domain, means whatever the stresses are being set up in sigma x or sigma y or sigma z is in on the both in the same domain, either the direction as well as the this kind of this area is there. Okay. And if we are talking about the other two components, like the either this shear stress component, if we are working in the x domain like tau xy or we can say tau xz, then always we found that the force is always in the y direction or force is always there in the z direction, but the domain is same. So you see here they have a real meaning, or sometimes we can say that the normal stress, there is no need to define sigma xx, sigma yy, sigma zz. You can straightway go and simply describe those things by sigma x, sigma y, sigma z. Okay, because we know that the nature of force as well as the domain, they have the same meaning and they are working in the same area of the matter of area is concerned. So like here we can simply judge based on our judgment. So it may be noted that in the case of normal stress, as we discussed just, you see the double script notation may be dispensed with the direction of normal stress, and the direction of normal to the surface of element on which it acts is the same, as I told you, sigma xx, sigma yy, sigma zz. Therefore, a single subscript, and that is what you see we are using always. If we want to describe any stress in the normal components, always we are going for sigma x, sigma y, sigma z, while in other components always we need to choose that actually how these other stresses are being set up, and for that, like for the shear stresses, because it's a plane stress, you see this stress is plane stress, not the axial stress. So always we need to the subscript just to show that what is the domain and what is the direction of the force is, and that's why you see always the shear stress components are being discussed in the two coordinate system. As you see here in this slide, we can see with the shear stress component the single subscript notation is not practical, as I discussed, because of such stresses are in the direction of parallel to the surfaces on which they act. So we therefore have two directions to specify that of the normal to the surface and the stress itself, means what is the domain and what is the direction of the force is. So like you see here, we can see that if we are working in the Cartesian coordinate, then we have this shear stress component. If the x domain is there, then this is sigma xy and sigma xz. So this is for the x domain, and if you are working in the y domain, then we have this tau yx and tau zx, and this tau yx and tau yz, and if you are working in the z domain, then we have the two different shear stress component, that is the tau zy and tau zx. So here you see that things are pretty simple, because you see there is no need to describe the two subscript for the normal stress component, but this is always essential to describe two subscripts for shear stress, because it will give you a clear cut physical phenomena about the shear stresses, that how they are being well set up within the system, irrespective whether it is a Cartesian coordinate or if you are talking about this polar coordinate or the cylindrical coordinate in which the r theta z is there. So we can say that if you are working in this r domain, that means you see the cutting plane is just perpendicular to the r, then we have this this tau r theta or tau r z, or if you are working about the theta domain, then we have tau theta r or tau theta z, or if you are working, or we can say if our domain is the z which is just perpendicular to the normal surface of the z domain, so we can say tau z theta and tau z r. So these are, you see the 6 different stress component which are there, and for which we need to describe in two different domains, irrespective whether it's a Cartesian this Cartesian coordinate system or whether it's a cylindrical or we can say the polar coordinate system is. So this is, you see, the normal stress. In the previous case, you see here this normal stress component is there, or like here you see in the cylindrical coordinate or in this this axis, we can see that here the sign convention, we can see that actually either the normal stress component or the shear stress component, always we need to go with the physical concept of this. So now you see, come to the main point, that in the Cartesian or the polar coordinates, if we want to combine the stress, you know, like we have the normal stress component, we have the shear stress component, how we can combine on a unit cube, because you see, you know, like as we have discussed that the unit cube is a very symmetrical object. So here you see, just focus on this diagram, which has the all three mutually perpendicular axes. The triaxial part is there, in which all three, you see, the stress components are there in x as well as y as well as z. So if you are working in the Cartesian coordinate system, then you can see here, these are my three different normal stress component. See very carefully here, we are only considering the tensile stresses because they are all going towards this outward direction. Okay, so here the sigma x, which is you see in the x direction, sigma y, which is you see in the vertical direction as you see, and sigma z, which is exactly in the z direction. So this is my normal stress component, okay, which are well set up within this unit cube. And if I add these things with the shear stress component, so you see here, if we are working in this domain, which is my z domain, as you can see, this is my z domain. So in that z domain, what the shear stress component are? Tau zy, because y direction is top of side, so tau zy, because the z is, this is my the area where you see the cutting plane is there, the normal to the cutting plane. So this is my tau zy in the vertical, and this is in horizontal way tau zx. Similarly, you see, if you are going towards this one, where you see this x domain is there and sigma x is there. So in the x direction, you see we have two shear stress component, tau xz and tau yz. So here you can say that actually xz, because it is going in the x direction, the stress is there, and it is going in the y direction, the stress is there. Okay, so this is showing the direction, this the other subscript x, z and z, but here we are always talking about this. Okay, and if you are you know, like going towards the other domain, then we'll find that you see here we have tau yz as well as the tau yx. Okay, so as we have seen here, that as well as the normal stress component or this shear stress component, if we want to combine those things in these three domains, x, y and z domains, we can straightway combine, and the combination of these stresses, because you see now we have 6 components from the shear stress, we have 3 components from these normal stress. Okay, so we have now total the 9 components, and if we want to define these 9 components, here you see this is the real diagram in which we can see that how these normal stresses as well as the shear stresses are being acting, what is the combination of these stresses at a particular point in these 3 domains. So here you see here, if you are talking about the z domain, then we have sigma zz, tau zy and tau zx, and if you are talking about the x domain, then we have sigma xx, tau xz and tau xz and tau xy. Or if you are talking about this y domain, in which you see we have the sigma yy, tau yz and tau yx, means that you see, you know, like these are the real 9 components just to describe the stress, the state of stress in the Cartesian coordinates. Similarly, you see, you know, like the similar 9 components we can also describe in the Cartesian polar coordinates, or we can say the cylindrical coordinates in r theta z. So here you see here, we can see, as we shown above, the normal stress and the shear stress components indicated on a small element, okay, in this material separately has been combined and depicted on a single element. So here pretty simple, these are my normal stress component which are acting in r, this sigma r, okay, or sigma theta or sigma z. And if you go to the shear stress component, then you have, if you are working on this theta domain, then what we have, tau theta z and tau theta r. If you are working in r domain, then we have sigma rz and sigma r theta, and if you are working in z domain, then we have tau z theta and tau z r. So now means that we have 9 different components, either irrespective of the Cartesian coordinate or irrespective of this polar coordinate. We can simply describe the all 9 components combinedly in this polar coordinates also, or cylindrical coordinate like this. This is the, you know, like as I told you, the theta domain. So in the theta domain we have sigma theta theta, or we can also, I told you that there is no need to go to the 2 subscript. So only one subscript is essential to describe this normal stress component. So we have the sigma theta here, sigma r here, or sigma z is here in theta, r and z domain for normal stress component, while for other 2 shear stress component, if we are there in the theta domain, then we have tau theta r and tau theta z If we are in the Rx domain, then we have tau Rz and tau R theta. If we are in the Z domain, then we have tau Zr and tau Z theta. So here means all three directions, in every direction or in every domain we have three different components. So all in all we have total 9 components. So if you want to define the state of stress, at least the minimum components which we need are the 9 components, as we have discussed in the Cartesian and the cylindrical coordinates. So by the state of stress at a point, we mean an information which is required at that point, such as it remains under equilibrium positions under the application of these forces, or simply a general state of stress at a point involves all normal stress components together with all the shear stress components as shown in the previous figure. So that's what you see we have. If we are talking about a general state of stress for any point or for any object, at least as I told you, the 9 components are there which are involving 3 normal stress component and 6 shear stress components. And then you see, this is a general phenomena that the state of stress at a point always needs 9 minimum components to define the state of stress at a point. Like you see here, the sigma x. Here, if we are working in the x domain, so this is for the x domain, sigma x, tau xy, tau xz. If we are working in the y domain, sigma y, tau yx, tau yz. Or if you are working in the z domain, then we have the sigma z, tau zx, tau zy. Means here, if we are discussing about the stress component at a particular point, always it needs 9 components. Means you see all 3 different directions are there. So the stresses are always be known as the tensor stress. That means you see it is neither scalar quantity nor vector quantity, it is a tensor quantity. So that's what you see. To describe a stress at a point, we need at least 3 cross 3 matrix, or we can say the total 9 elements, for which we can say that how the stresses are being set up within the object, or how they are playing if the this load application is there on an object. So you see now, it is a general phenomena of the stress. Now you see, because as we have discussed in the previous case, you can see here, if you see this figure is a well symmetrical figure in the Cartesian in the polar coordinate, or if you go to the Cartesian coordinate, this figure, or we can say this unit cube, is well stabilized, or we can say well equilibrium figure in which the symmetricity is there. So if we are talking about these kind of things in which the symmetricity is there, then we don't have to need all those 9 components to describe these stresses. So what we can do here, we simply apply these symmetrical conditions to these equations, and we can reduce all 9 components, because you see at every point, if we are analyzing or if we are calculating these 9 components, then it is pretty tough to check the stress every time, because you see if the load application is changing, how these 9 components are changing, or you see which one is dominating, which one is not dominating, is pretty tough. So you see what we are doing here to make simplicity, what we are applying certain equilibrium conditions, or we are choosing the element so that actually it has certain symmetricity towards either the x direction, y direction, or z direction in the Cartesian coordinate, or r direction, theta direction, or z direction in the cylindrical coordinate. So here you see now, the first case, if we apply the conditions of the equilibrium, if we have a point over which the summation of all the forces in x direction is 0, or the summation of all forces in y direction is 0, or summation of all forces in z direction is 0, means under the force application there is no no movement, or there is no deformation is there within those objects. Since we apply the force, there are internal forces are there and they are well established. That means you see our object is in equilibrium phase. Means that all the summation of forces, internal forces, if they are coming out of that, or the external forces if they are applying, the summation of all the forces in x direction, y direction, and in y direction and the z direction, they are 0. Or we can say, if we take a point like Q, among these points, means if we have pivoted this point Q, if we take the moment about this point in x direction, like summation of these mx or my or this mz, that means if you are taking the moment about x, y, or z axis, if you sum up those points, if it is 0, we can say that it is well under equilibrium conditions. So for that, Since you see here the two things are there, one, whatever the forces or the moments which are applying on the object, they are well set up, the all summation of the forces as well as the moments are 0, and we have the unit cube which has a symmetric geometry. So if you apply those conditions, then we can conclude that the shear forces which are applying in x direction tau xy or in y direction tau yx, means you see now what we are doing here, we are simply changing the direction of force, and we are simply changing the direction of force as well as the domain. So if you are talking about those things, then we can say that sigma, the tau xy is exactly equals to tau yx, because you see if you are talking about the frontal part and if you are talking about the rear part, they have the symmetricity and there is no change in the force. We can say whatever the parallel forces are there which are being set up in two different domains as well as the two different directions, they are equal, because they are equal and opposite. That's why you see we can say that the summation of forces are equal. So similarly, you see if we apply this symmetricity to this object, we can say tau xy equals to tau yx, tau yz is equals to tau zy, and tau zx equals to tau xz. So you see here only these conditions are applicable when we have a symmetric geometry first, and when we have a this summation of the forces, the reactive forces and the applied forces in x, y and z are equal, because they are, that's why you see the Newton's third law says that if reaction and actions are equal, then we can say yeah, the body is in equilibrium position. Otherwise there is always, when you apply the force, either the deformation is there, motion is there, whatever the things are there, so we cannot apply these conditions here like that straight away. Okay. So now you see if you like conclude that part, then we will find that there are 6 components instead of 9 components. Only we need 3 normal stress component, sigma xx, sigma yy, sigma zz, or we can say sigma x, sigma y, sigma z in the normal stress component, or we need only tau xy, tau yz and tau zx for that. That means you see if we are talking about a 2-dimensional way, only you see sigma x, sigma y, sigma z, 3 different directions stresses are there, and we have you see the 3 different components of the shear stress like these things, and they are well set up if we have the two previous conditions are applied. Means you see now like just 6 components are like well defined, and we can say that actually the stress, the tensor stress is well defined if the object is symmetric by 6 different components, 3 normal stress, 3 shear stress component. Now you see come to the another point in the shear stress only, that complementary shear stress. Like as we have discussed that the shear stress is a plane stress. Plane stress means you see like it is always acting in either xy, yz or zx plane, as we have seen in the previous part. You see here these 3 the shear stress is there, so tau xy, tau yz and tau zx. So if you want to analyze these things, what we need to define the existing shear stress on any 2 sides of the element, this, that or whatever you see in all 3 sides of these things, induce and complementary shear stress on other 2 sides of element to maintain the equilibrium. Like you see here, if we are just chosen AB and CD in which you see the tau is acting, so on this we have this object and the shear stress is just going across this, they are parallel forces as I told you, so they are just going in these directions, so they will just tend to move this object in the clockwise direction, just it will move like that. So we require an opposite component to compensate this or to resist this motion. So whatever the stress component, because as we have already discussed that it is well equilibrium position to like, so that's what we need to define a new component. So whatever the resistive components which are coming due to this plane stress, this one plane stress, or we can the shear stress is known as the complementary stress. So here you see, you can see that in AD or in this CB, whatever the tau dash is coming, this is nothing but the complementary shear stress. So on plane AB or CD, as we have seen in the previous figure, the shear stress tau was acting, and due to that the object or the body is tend to move towards the clockwise direction, while to maintain the static equilibrium always we require, it must be, we require the plane AD and BC must be act towards opposite direction, that means in the anti-clockwise direction, and to do that we need to like consider a shear stress that is known as the complementary shear stress, and we are always denoting by tau dash. So we shall see that the tau dash, which is known as the complementary shear stress, as we discussed, would come out equal and opposite to tau. Then only we can maintain the equilibrium. Then only all those components, whatever the conditions are there, it is applicable to that. And let us prove that this thing for general case is, as you see, this is there, that if we are talking about previous case, so what we need here, only instead of 9 components, 6 components are there. In the 6 components we have this, like the sigma x, sigma y, the sigma x and sigma x in the x direction, while sigma y and sigma y is there, because now we are talking about a plane stress in which x and y is there. So whatever the stresses are being set up in xy plane, now this figure is showing here. So if we are talking about this, what we have a unit cube which has the total the width in x direction is delta x, total width in y direction is delta y, and if you are working in the x domain, that is, you see the x domain, what we have 2 components. One is the sigma x, which is the normal stress component. One we have the tau xy, here in this the downward direction, or tau xy, which is the upward direction. So you see here, since tau xy, because the x is the domain, y is the direction in upward as well as the lower direction. So here these 2 components which are on this side of this element in the x domain, or these two elements, the sigma x and tau xy, are working on the other side of the element. Similarly, you see, we can see that this component is well maintained because of the other 2 components are working in the y direction, like sigma y is there in the vertical directions. So one is, both are going in the opposite direction, and they just want to maintain the equilibrium around the point A. And similarly, you see, we have tau yx and tau yx, because we are working in the y domain, so y is there, and x because they are going in the parallelly to the x directions. So these 2 shear stress components are there. So you see, if we are discussing about a simple plane part where the xy is there, how many stress components are there? Total we have 2 normal stress component and 2 shear stress components. So only 4 stress components which we need. No need to go for all 9 components. Only 4 these stress components are there. 2 of the normal stress, sigma x and sigma y, and 2 tau xy and tau tau xy and tau yx is sufficient to describe these stress component if we have the unit width sigma x and unit width this sigma y in corresponding x and y direction. And now you see, if we are saying that it is maintained equilibrium, only possible if whatever the forces are there at around these structure, and whatever the moments are there about this pivoting point O is 0. So now you see, as we discussed, first of all, the sign conventions are there for the shear stresses, because you see, for tensile for this normal stress component, we already discussed about the sign convention. Just to remind you again that we have, if the tensile forces are there, if the pulling is there, we always consider the positive stress. If the compressive stresses are there, we always consider the negative sign convention for the compressive force as well as the compressive stresses. So similarly, you see, here the sign conventions for the shear stress, the direct stress if you are talking about, or the normal stress, thus positive and negative for this, or the shear stress if it is tending to move towards the clockwise direction, means you see, if object is moving towards the clockwise direction, always see that if whatever the stress components are there which is always trying to force towards the clockwise direction, consider the positive. So, and if you see the restive, the complementary, as we have seen in the previous case, the complementary shear stresses which just tries to oppose that part and tries to rotate the object in the anti-clockwise direction, consider the counterclockwise, or the, we can say, the negative direction is there for that. So sign convention is always gives you the resulting force applied on any element which is in equilibrium, always in x or y direction, just gives you that actually whether the shear stress is applying in the positive direction or not, or complementary shear stress is applying in the positive direction or not. So although you see the normal and shear stress component are not in those shown in the present part, but you can simply conclude that actually if the restive forces are not applying in another part, then we cannot maintain the object in the equilibrium manner. So that's what you see, sign convention is very, very important to see those things. But to apply the or to maintain the equilibrium position of those, you see, the object, always certain assumptions are there. If those assumptions are applied, then only we can say that yes, this object is well maintained, under the equilibrium conditions, and whatever the forces or the moments are applying, they are well set up within the object. First, the weight of the element is neglected. We are not considering the weight here, because if we consider the weight, definitely you see, due to the gravitational acceleration, there is some more stresses are there, and these stresses you see sometimes, because the another force application is there and the weight is there, these non-uniform stress distribution is there, and because of that you see if we want to define the stress by either the Cartesian or this cylindrical coordinate, which is very tough and very complex, because the stresses are different at different points, because the displacement of each molecules, they are different, and the resistive forces are different because of the self weight of the element. So the first and the most foremost this assumption is always neglect the weight of element. So that's what you see in further whatever we are going to discuss, either this bending of beam or shear stress of any like the twisting part or torsional of shaft or any like either the deformation, stress, strain, always we neglect the weight for that of the object, just to make easy of the analysis. Second, since the element is static piece, because you see like under the application we always assume that there is an static part is there of solid body, the moment applied to on these things must be in equilibrium. That means you see like as we discussed in the previous case here in this figure, whatever the moment is applying, because these forces are there you see, and if the shear stress components are working, there is a moment through this point, so they are well set. That means you see this object is in a static way, so we need to assume that whatever the moments are applying on these object because of the shear stress or normal stress component, they must be well set up, they must be equilibrium, or we can say the summation of all moments in different domains x, y, z, they must be 0. And second, you see like the third assumption is, let us consider the axis through point O, resultant force associated with the normal force acting on the sides of element passes through the axis, therefore there is no moment. That's what you see, I told you that whatever the moments will come in this kind of object, where you see this if you are considering the point, the origin at centrally, and these normal stress component in x axis, y axis or z axis, if these axes are passing through origin, then there is no moment because these axes are passing. But as well as the shear stress component, because they are the parallel to like these axes or these domains, there is always you see that's what you see, due to the moment they are tending to like rotate this component. But we need to assume that whatever you see the reactive as well as you see the active forces are there, or these stresses are there, they must be well set up, and the moments about O must be 0, like that. So now you see we can see that now the forces on top and bottom surfaces produce a couple, as I told you, because of the shear forces, which must be balanced by the forces like you see tau yx into the total domain dx, dz and dy is equals to tau xy into dx, dy and dz. So if they are well balanced amongst these, you see now if you go to back, you see in this figure, then you will find that because of this tau xy, this tau like the tau yx into dx, dy and dz on this particular surface, or similarly you see this tau yx, which is exactly you see like in the bottom of that, if it is well balanced, we can say that actually like it will always balance those things, and we can say the symmetricity is there because of those things. Again, the moments are 0 or the forces are 0, we can conclude that tau yx is exactly equals to tau xy, and this is one of the symmetric condition that you see in the previous case we have discussed, that if all the moments are 0, all the forces are 0, we can say that tau yx equals to tau xy, or we can prove by this way also. Or similarly you see, in other words, the complementary shear stresses like are equal in magnitude and the same form, like they simply form the relationship that can be obtained by the other two pairs of the shear stresses in the two different domains, like tau zy is equals to tau yz, or tau zx is equals to tau xz. So you see here, irrespective of whether we are working in any of the domain, always the shear stress components are equal in the respective directions if we consider the symmetricity, or if we consider that you see whatever the objects are there, like they are well like under these forces they are well maintained and the equilibrium. So that's what you see like we discussed about all these forces, that actually if we have a general state of stress, at least we need the 9 different components in which the 3 like the normal stress components are there, and 3 and 6 the shear stress components are there if we want to describe the general state of stress. But these, and even if we apply that the symmetric conditions in which you see we need only 6 components to describe the stress, 3 normal stress and 3 shear stress component. But these, whatever we discussed in this, the domain was very symmetric as we have seen. You see, only at the outer part where the symmetricity is there, where you see X domain or Y domain or Z domain, these forces are well set up. But if we want to consider the stresses at the oblique plane, that means you see, if we cut the plane at theta angle, now if we want to check that what the internal setup of the stresses are there, then how, these normal stress as well as the shear stress components will take place, and you see how, what kind of analysis which we need to take, which we need to consider, because at that point we cannot say that the moment is 0, because this is the internal part of an object, or we cannot say that all the summation of forces are 0. So, what is exactly the relations are there, and in between these two components of the stresses, normal as well as the shear stress component in xy plane or in triaxial form xyz plane, which we are going to discuss in the next lecture. Thank you. Bye bye.